Shri Gurubhyo Namaha, children. We welcome you for our online teaching academy, Eka Laiva. Today we are going to continue with 12th standard physics state board, chapter number 4, electromagnetic induction and alternating current. We are going to discuss today power in AC circuits, power factor and wattless current. So let us start with power in AC circuits. So what is power? Now the definition for power is, it is defined as, power is defined as the rate of consumption of electric energy. So how do you consume electric energy in a particular circuit? That is defined as power. Okay, ma? So simply in a formula we can give power is nothing but it is the product of voltage and current. You would have read this in your lower classes. We have the formula for power as voltage into current. Okay, ma? Right. Now we are discussing about AC circuits, right? So in an AC circuit, since the current is alternating, the voltage and the current, they vary continuously with time. So let us calculate what is the power at any instant, and then when you average it over a complete cycle, you will get the average power. So that is what we are going to do. That is how we are going to calculate the power in an AC circuit. First, let us find out the formula for the instantaneous value of current. Then we average it to get the total value of power. Okay, so let us start the derivation part of it. Let us write the alternating voltage and alternating current equation. Okay, so we know the instantaneous voltage equation is given as V is equal to Vm sine omega t, and I is equal to, let me have a comma, so I is equal to Im sine omega t plus phi. So phi represents the phase angle between the current and the voltage. Okay, so to find out the instantaneous power, okay, so this is the instantaneous voltage, this is the instantaneous current. So to find out the instantaneous power, P is equal to V into I. So what is V? V is Vm sine omega t into Im sine omega t plus phi. So I rewrite this as Vm Im sine omega t into sine omega t plus phi. Okay. Now I'm going to simplify this equation. Vm Im, this is sine omega t, as such I will write. Now this is of the form sine A plus B. So what is sine A plus B, children? Sine A plus B is sine A cos B plus cos A sine B. Okay, ma? Right. Now I'm going to take this sine omega t inside. So the equation becomes Vm Im sine omega t becomes sine square omega t into cos phi. Okay, right? To the second term I'm bringing this sine omega t. So sine omega t, again I have cos omega t into sine phi. So this is the equation. Okay, now the steps are continuing, but in your textbook they have not given the entire steps, and after the simplification they have given the formula for average power. Average power is given as Vm Im cos phi into half, because the simplification steps involve a lengthier process. So what is that they have said is, they said that the average of this sine square omega t for a cycle is taken as half, okay, and this sine omega t cos omega t is averaged to 0. So when this is going to be 0, the whole term gets 0, and here it is sine square omega t, which is equal to half. The cos phi remains as such, so the average value of power is Vm Im cos phi into half. Okay, so this half, in this denominator you have 2, which can be written as root 2 into root 2. So I separate this as root 2 into root 2. I'll just I'll write as Vm by root 2 into Im by root 2 into cos phi. So now this we know what is Vm by root 2. Now here this formula we have already read in the introduction of alternating current. So this is nothing but Vm by root 2 is nothing but Vrms. Similarly, Im by root 2 is Irms. Okay, so this I have already discussed in my previous videos. What is Vm by root 2? What is Im by root 2? You can refer that. Okay, ma? So power average equal to Vrms, Irms, cos phi. So this is the equation for average power. Now this average power is also known as true power. Now let me write this in words. So average power, or it is also called as true power. Okay, average power or true power is equal to this Vrms, Irms is nothing but apparent power. Okay, apparent power into what is cos phi? Cos phi is nothing but, you call it as power factor. So this is the formula. Average power equal to Vrms, Irms, cos phi. Here apparent power, Vrms, Irms represents apparent power and cos phi represents power factor. Okay, so this is a very, very important formula. Now, based on this, I'm going to discuss some special cases. Okay, so based on what type of circuit is this? Okay, so let us start with the first special case. Let us take a purely resistive circuit. Purely resistive circuit in the sense we connect a resistor to an alternating source. Okay, so in that case, we have already read that the phase angle between voltage and current is 0. Okay, and the circuit is said to be purely resistive circuit. So phase angle between current and voltage is 0. So here in this formula, cos phi represents the phase angle between what? Current and voltage. So this angle, if it is going to be 0, substitute phi is equal to 0. So in that case, cos 0 becomes 1. So what will be the average power for a purely resistive circuit? So for a purely resistive circuit, power average equal to Vrms, Irms. Is it clear? So this is the first case, right? Then the second case is when we consider the circuit to be purely inductive or purely capacitive. Okay, so in a purely inductive circuit or in a purely capacitive circuit, we know that the phase angle between current and voltage is plus or minus pi by 2. I am just recalling what are the concepts we have already read. Okay, so in an inductive circuit or a capacitive circuit, we have already learned that the phase angle between the current and the voltage is plus or minus pi by 2. Plus or minus pi by 2 in the sense it is 90. So when you substitute cos 90, okay, here again cos 90 you substitute. So when I substitute cos 90, this becomes 0. So hence power average is 0. Where for a purely inductive, okay, inductive or capacitive circuit. Okay, so power average is 0, right? The next case is for a series RLC circuit. We know the phase angle as tan phi equal to XL minus XC by R. So what is phi? Phi will be tan inverse of XL minus XC by R. So in this case only we have derived what is the value of average power. Average power in this case will be, we have already derived, what is that? VRMS or VRMS cos phi. Okay, ma. So this is the case of RLC circuit. So we started our derivation considering RLC circuit only. The derivation, in the introduction I've said the alternating voltage and the alternating current in a series RLC circuit is given as. This is where I started. So we arrived at the value of average power to be VRMS, IRMS, cos phi. This is the answer for average power. Okay, so VRMS, IRMS, cos phi. Okay, this is the case of an RLC circuit. And the fourth case is, again we are taking an RLC circuit, but this time RLC circuit in resonance. Now we have already discussed this case. In resonance, we know that XL is equal to XC, right? So in that case, the phase angle XL is equal to XC means we know, we found out that the current is maximum and the circuit becomes a purely resistive circuit where the voltage and the current are considered to be in phase. In that case, the phase angle will be again 0. So when the phase angle is 0, cos phi is equal to 1. So here also I have the average value of power to be VRMS, IRMS. Okay, so this is with RLC in resonance. So these are the 4 cases which gives the information about the power, okay, which is based on the formula average power equal to VRMS, IRMS, cos pi, or it is apparent power into power factor. Apparent power is VRMS, IRMS, and power factor is cos phi. Okay, ma? With this, we are moving on to the next topic, wattless current and wattful current. Okay, now here, again, let us consider an AC circuit in which there is a phase angle of phi. Now here, there is a phase angle of phi between VRMS and IRMS. Okay, and here we assume, according to this diagram, we assume that the voltage is leading the current by a phase angle of pi. Now this phasor diagram we have discussed in an inductive circuit. In an inductive circuit, you know that voltage leads current. So here also let us consider the voltage is leading current by a phase angle of pi. Okay, now I am going to resolve this current. Okay, resolve this current into 2 components. Now when this is the current phasor, right? Now when I resolve this current into 2 phasors, the angle phi, which takes the value of IRMS cos phi, which is considered to be in phase with VRMS. Okay, so this is one component, and perpendicular to this you have another component which is called as IRMS sin phi. Try to understand the diagram very clearly, children. This current is resolved into two factors. Now, one is along VRMS, which is taken as IRMS cos phi. Whenever you resolve a vector, you resolve along horizontally and vertically. Now, here, this is considered to be cos phi because it is adjacent to this phi. That is the angle. That is, it is adjacent. Whichever is adjacent to the phase angle, you take that value as IRMS cos phi. Since the phasor is current, we take it as IRMS cos phi. And perpendicular to this, we have IRMS sin phi. So I'm going to name this now as wattless current and wattful current. So first let us take the component IRMS cos phi. So this IRMS cos phi here, look at this diagram. Now in this current and voltage, they are in phase with each other. So they are considered to be, the current is considered to be an active component which accounts for the power, or it accounts for useful power. Okay, so this power, no, so the power consumed by this, so what will be the formula for the power consumed by this? We know the formula for power is nothing but V into I. Here V is VRMS and I is IRMS cos phi. So the power consumed by this is given as VRMS IRMS cos phi, and this power is called as wattful current. Okay, now let us come back to this. Now this is a component perpendicular to this. Okay, so this has a phase angle of pi. So what is the difference? I mean, what is the angle between this voltage phasor and this current phasor? Now this is VRMS. Forget about this. You consider this voltage and this current. Okay, so when I consider what is the angle between this VRMS and IRMS sin phi, it is 90 degree. Okay, so this component is called as reactive component, and the power consumed, now here phase angle becomes pi by 2 here, so cos 90 will be 0. So what is the power consumed here? So the power consumed here is considered to be 0. So this is called as wattless current. Okay, so wattful current and wattless current. Okay, and they define, so what is wattless current, in which circuits you will have this wattful current and excuse me children, wattless current. Now let us consider a circuit. Let us consider the first circuit, which is a pure resistive circuit. Now again we know that in a pure resistive circuit, the phase angle between the current and the voltage is 0. So in that case, cos 0 becomes 1. So the power is said to be VRMS IRMS. So whenever we have the power value to be VRMS IRMS, you call that circuit as what mean? You call that current which is produced as wattful current. So which circuit will produce wattful current? An AC circuit with a pure resistor. A pure resistive circuit will produce wattful current. Okay, where this wattless current happens? Now this wattless current will happen in a purely inductive circuit or a capacitive circuit, because whether it is an inductive circuit or a capacitive circuit, we know that the phase angle between the current and voltage is pi by 2. So in this case, so whether in an inductive circuit or a capacitive circuit, wattless current occurs. Okay, so this is about wattful current and wattless current. The next we are going to do is what is called as power factor. So we are going to discuss three formulas, okay, to define what is power factor. Now we know the formula for average power, or this can be written as average power or true power. Okay, ma? So for the formula for this is VRMS IRMS cos phi, or I can also simply write as VI cos phi. This also can be written. So I'm going to define now. This VRMS IRMS is nothing but, I already told you, apparent power. VRMS IRMS is apparent power and cos phi is power factor. So I'm going to define this power factor in three ways. So the first way is, power factor is nothing but what? Now in this equation, what is power factor equivalent to? This is equal to cos phi. So what is this cos phi? Cos is nothing but cosine. Okay, ma? Cosine of the angle of lead or lag. Okay, whether the current is leading the voltage or the current is lagging the voltage, whatever it is the angle between voltage and the current. So the cosine of the angle between the voltage and current is represented as cos phi, which is termed as power factor. Okay, ma? And the second way of expressing power factor, the second way of expressing power factor is R by Z. So this you can refer the diagram. Okay, in an RLC circuit, in our textbook, we discussed this case. Okay, where we talked about voltage and impedance triangle. Figure 4.53. Now the impedance triangle, this is how we drew the impedance triangle in an RLC circuit. Okay, so let me extend this arrow. So here, now this is the phase angle. Now this is O, this is A, and this is E. Okay, now this is R and Z. Now R is the resistance and Z is the impedance. Now this is XL minus XC. So this is the impedance triangle. Now again here we have phi, which is nothing but called as power factor. When I take the cos phi of this, cos value of this, what is cos theta? Cos theta is adjacent side by hypotenuse. Adjacent side is R and hypotenuse is Z. So this is nothing but R represents resistance and Z represents impedance. So this is also one of the way of representing power factor based on impedance triangle. Okay, ma? And the third way is from this formula. Okay, we know. Now we know that average power or true power is equal to apparent power into power factor. So from this, let us bring this power factor to the left hand side. So power factor equal to, this will be average power or true power. Average power or true power by, what is the denominator? I have apparent power. Okay, so average or true power is, I have already told you, this can be written as VI cos phi. So this can be also written as VI cos phi. Now apparent power will be simply VI. When I cancel VI also, I have cos phi, which is nothing but power factor. So these are the three ways of representing power factor. So for a pure, like once again, for a pure resistive circuit, we have the power factor to be equal to 1. Okay, for a pure resistive circuit, because phase angle between current and voltage is 0. Okay, so if it is going to be 0, cos 0 will be 1. So power factor for a pure resistive circuit, once again it is going to be, it is going to be 1, because the phase angle between voltage and current is 0. Suppose if it is for a purely inductive or a capacitive circuit, since the phase angle between them is pi by 2, that is plus or minus pi by 2, we have the power factor to be having cos plus or minus pi by 2, which is equal to 0 once again, right? Then the third is for an RLC circuit, we have variation between 0 and 1. So the power factor for an RLC circuit will vary from 0 and 1. Okay, so these are some of the points about power factor. So go through the concepts, refer your textbook for more information. See you in the next video, children. To subscribe for our online lessons, please press the subscribe button and you will be receiving our latest updates. Thank you, children.